Alright, I believe, yeah, this is recording now. Let's take a look at the second part of our uniform motion problems. Um, Here we have in problem 6, the speed of a moving walkway is about 4.75 feet per second. Walking on the moving walkway, it takes Karen a total of 40 seconds to travel 95 feet with the movement of the walkway and then back again against the movement of the walkway. What is Karen's normal walking speed? So the only place I've ever seen these moving walkways is in airports, and so it's very similar to the current problems if you're in a boat when your boat is traveling with the current versus against the current. So you can think of the if the sidewalk is moving in, say, in this direction, and if this is Karen's starting point, then what's going on is she's walking out a distance of 95 feet, and then for whatever reason turning around again. So when she's walking in this direction, she's walking with the speed of the walkway. When she gets to this point, she turns around and she's walking the other direction, which is against the walkway. So if this is the speed of the walkway at 4.75 feet per second, then, and if we let x be Karen's normal walking speed, we can visualize the problem a little bit better with a picture. So when she's walking with the walkway, her speed relative to a person watching is x plus 4.75 feet per second, and when she's fighting against the speed, it's slowing her down. So one way it feels like she's moving really fast to her, and in the other direction, why she's trying really hard to walk fast, and it's fighting again. You're running uphill against a treadmill type idea that she's fighting the speed of the walkway. So now we have to think, how are we going to get a relationship from all of this? And the idea is that we pick something to work with, either and typically it's either distance or time, and then furthermore we look and see, well, are we going to set two distances equal to each other, or are we going to look at a total distance? Then if it's time, again, are we going to set two times equal to each other, or it's a total time? So I can see two approaches. Somebody might come along and say, well, the distance that she walked with the walkway is the same distance against, so you could set those two distances equal to each other and try to do that. But the problem is, we know the total time, but we don't know the length of time that she takes to walk with the walkway, or the time against the walk. We only know the total time. So that total time is probably the route to go first, to attempt. And if we don't get anywhere with it, we need one equation and one unknown. And if we come up with two unknowns, then we've got to try the other way. So if we look at the total time, that total time to complete this round trip was 40 seconds. Part of that time, Karen was walking with the speed of the walkway, and part of the time, the rest of the time, she's walking against the speed of the walkway. So yeah, this is going to work out pretty nicely, I believe. Alright, so we can replace the total time with 40 seconds. And we know our relationship is that time is equal to distance divided by rate. So the distance divided by the rate for the part of the journey, the trip of the journey when she's walking with the walkway, and the distance divided by the rate when she's walking against the walkway. Alright, now the distance for each numerator is the same, the 95 feet. So we've got 40 is equal to this 95, and in this numerator 95. Now when she's going with the walkway, that's addition. Karen's normal walking speed in addition to the walkway, and when she's walking against it, we model it as a subtraction because she's fighting against the walkway. Alright, so we have a rational equation. We have variables and denominators. So we're going to get a quadratic. Alright, so let's take this. Let's take our equation, and now normally the most difficult part is setting it up, but in this case this equation is going to be a little bit of a challenge for some. Alright, so we need a common denominator, and this denominator is 1, this is x plus, this is x minus, so we need both of those factors in every denominator. So we're going to multiply each term by the number 1, but we're going to do it in such a way that it gives us the denominator that we want. So over here, if we add the 4.75, that's multiplying that 40 by the number 1 because the numerator and denominator are the same, and that gets me part of the denominator I want, so I multiply it by x minus 4.75, and there's the denominator that I want on the fraction for that term that's on the left hand side. Now for this first term on the right hand side, we've got the plus and we need the minus. So we need x minus 4.75 and x minus 4.7. The numerator and denominator have to be equal to each other for this fraction to reduce to 1. And now in this second term on the right hand side, we've got the minus, but we need the x plus 4.75. Alright. Now all of my terms have a common denominator. So if I multiply every term by that common denominator, it will clear all of my denominators for this equation. And so what I'll have is just the numerators. And here we can see that we're going to have two of these 95x's, but the minus and the plus are going to cancel each other out. And that guy's a plus. Alright, so over here on the left hand side, this is a special product, our a plus b times a minus b, which we know is a squared minus b squared. So these first terms, when I multiply them together, it's x squared. The middle terms cancel each other out, and we have minus whatever this 4.75 squared is. Alright, so when I distribute this, I have this 95x, but this minus this product, and then over here the plus on that second term when I distribute are going to cancel each other out. So to save writing, you would have had minus 4.75 times 95, and then over here plus 4.75 times 95, and those just cancel each other out. So let's take a look. We've got 40x squared, and I'm not going to try to, normally I look for ways to make these numbers smaller just to make the arithmetic easier, but since I have a calculator here, I'm not even going to bother to try and do that. When I distribute that 40, I've got 4.75 squared. So this guy is a minus 902 and a half, 0.5. And the 95 and 95, 190, right? So, for this quadratic equation, I'm not going to bother to even attempt to factor it. I'm just going to jump right in and use the quadratic formula. And most likely one of the values is going to be negative and the other positive, and I'll want that positive value. So let's put parentheses around our numerator and take the opposite of b. This A is 40, B is negative 190, and C is this negative 902.5. So the opposite of negative 190 is a positive 190. And I'm going to add, even though I know that it's plus or minus, I believe that the minus would give us a negative answer. So I'm going to start out with doing the positive one first. And if we have to, we'll come back and take a look and see what's going on. When we square, this is b squared. When we square this number, it's going to be a positive value, but I'll go ahead and plug it in as a negative. But we know that we could get away with just plugging in the calculator a positive 190 squared, but just to illustrate a direct substitution. Now, my a value is, because it's minus b squared minus 4ac, where a is 40, and my c is this negative, and don't lose that negative sign. Alright, so this guy is my entire numerator, right? Yeah. Let's make sure I have a parenthesis there at the beginning. Yeah, I've got a parenthesis at the beginning and at the end. So that's my entire numerator. My denominator is 2 times a. 2 times, I don't need the parenthesis because 2 times 40 is 80. I know what that is. So let's see what we get here. Alright, so I'm getting that Karen's normal walking speed is 7.6, and if I round it to 2 decimals, 7.69 feet per second. Now, just to illustrate, I suspect, let's bring up what we keyed in, and let's come over and make that plus, because it's plus or minus. Let's make this a minus sign. And I think it'll be negative and we'll just end up discarding it, but let's see. Yeah. So it doesn't make sense, she's not doing a moonwalk. She's not walking backwards. We throw out that. The quadratic equation is a good model, but we have to use it, use our reasoning skills and stuff with it. And sometimes we discard values that just don't make sense. So the 7.69 feet per second is what we're getting. Let's see if the key agrees with us. I cut and pasted it on here, I believe. Yeah, and to 2 decimals, 7.69 feet. So we got it. We got the same value as the key. All right. Let's move on to this next problem. We have a small plane can fly 200 miles per hour with the wind. Now, this time that 200 the plane flies less than that in calm wind. With the wind pushing it, it's accelerated, it's pushed it up to 200 miles per hour. See, last time we 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 knew how fast the walkway was moving. Here we don't know how fast the wind is. Just right off the bat, I can see that it's telling me the end result. It's telling me that the 200 miles per hour is with the wind, and here 150 miles per hour against the wind. The wind is blowing due east, and the plane takes off and flies due east. So the plane takes off into the wind, and normally that's what pilots do, is take off and fly into the wind. Fly due east to Indianapolis and returns to the same airport. So you have a round trip type idea. The total flying time for the trip was 4 hours. How far is the airport? So we have this airport, and we have Indianapolis, and when the wind is blowing due east, so this direction is east, and the plane is taking off going into the wind, right? The wind is blowing due east, the plane takes off and flies. No, wait a minute. I have that backwards. Let's come over. I don't believe the direction is really going to mess us up that much, but let's make this way east and this way west, like on a map. Alright. Now, the wind is blowing it to due east. So I'm assuming that means that it's blowing towards the east rather than from the east. I don't know when the weathermen give us wind directions how exactly that goes, but let's say that. And the plane takes off and flies due east. So actually when the plane is taking off, it's flying with the wind in this case. So even though I might have that backwards, I don't believe it's going to affect our answer either way, because we're trying to find the distance from the airport. So if this is the airport, then to the east of the airport is Indianapolis. And so the plane takes off and it's flying this direction initially, and then it turns around and flies back, right? Yeah. Now, when it's flying this direction with the wind, it's flying faster. So in this direction, it's flying at 200 miles per hour. Because when you're going with the wind is pushing you along. When you're, let's assume that during the entire trip the wind doesn't change direction and it stays the same magnitude. So now when you're flying against the wind, it's 150 miles per hour. Okay, so that helps us visualize, or at least helps me visualize the problem a little bit better. So again, we have to decide whether we want to work with distance or time, and whether we want to work set things equal to each other, or that idea that the total is the sum of the parts. And here it gives me a total, and so that's what I'm drawn to. Although, you know, when we do these, oftentimes there's more than one way to do a problem. So if you're doing your problems in some other way, but you're getting the same answers that we are, then you're fine. So our total time, there's two legs to this part. When you're flying with the wind, and that's towards Indianapolis, and when you're flying against the wind, when that's flying back to the airport, the way we've drawn it. Alright, so our total trip time was 4 hours. That's how much the total time in the air flying. We know that time is distance divided by rate. So the distance divided by the rate when we're flying with the wind, and the distance divided by the rate when we're flying against the wind. Alright, so let's see if we can, now that we have our relationship and equation, let's substitute in values and stuff from the problem that's given. We want to let x be that distance. How far is the airport? So the x is the distance from the airport to Indy, which is the same as the distance from Indy to the airport. Okay. So that's my numerator, and in each case, that distance on each leg doesn't change. Now, when you're flying with the wind, see, this time they gave us that total. Last time, our variable was that we didn't know Karen's walking speed. And although we don't know the plane's flying speed in still air, it's not asking us to solve for that. It's asking us to solve for this distance. So when you're flying against the wind, it's slowing you down, and that's 150. So this equation is going to be easier to solve than the last one. It's not quadratic like the last one was. All right. So let's get a common denominator, the least common denominator of 600. So let's multiply the left-hand side by 600 over 600. Let's multiply this denominator by 3 over 3, and this denominator by 4 over 4, right? So now, 150 times 4, let's check that, make sure. Yeah. So I've got the same, with every term having the same denominator, we can just focus on the operations in the numerator. So if we divide by 7, I'm sure that'll be a decimal number. Yeah. Alright, 342. Let's call it 86. Alright. Now remember that x was the distance, and that's in miles. So the distance from the airport to Indianapolis is 342.86. I wouldn't be surprised if we just, if they just end up calling it 343 miles. We don't have to get so precise. The nearest integer is typically going to be good enough with a distance. When you're on the interstate driving and those mile markers, that's just an approximation most of the time. All right, 343, 343. So with the speed of things, you may want it to the nearest tenth or the nearest hundredth or something, a little more accurate. When it's just approximating this distance and stuff, and the 342 is so large of a number, the 14 hundredths of a mile doesn't make that much of a difference. So they just rounded it. And I'll tell you, on problems and stuff on the directions, I'll try to remember to put on there to round it to the nearest integer, or round it to the nearest tenth, or tell you what to round it to. I should have probably for you had that on these problems as well. Alright, so I can't remember if we have 8 problems or 10 problems, so let's keep going and see here. While training for a triathlon, Susan rides her bike at a speed of 20 miles per hour, runs at a rate of 8 miles per hour. She spends, I thought for the triathlon with the tri there'd be 3 things going on, but it looks like there's just, oh yeah, wouldn't there be swimming? Huh. Susan spends 3 times longer riding her bike than she does running. One day she travels a total distance of 51 miles. How far does she travel on her bike? So, how far we're wanting a distance. It's giving us a total distance. So we've seen this on several of the problems that we have the total as the sum of the parts. So this total distance is split up between the distance that she rides her bike plus the distance that she runs. So this 51 miles is split up to some of those miles we're riding the bike and some of those miles we're running. And distance is rate times time. So we want the rate and the time with respect to when she's on the bike, and the rate and the time when she's on foot running. Now, on her bike, let's see, she goes faster. Yeah, on the bike is the rate is 20 miles per hour. And running, she runs at a slower speed, obviously, and we've got 8 miles per hour. Now, the time. She spends the longer length of time riding her bike. So if we let X be the time that she runs, then the time that she rides her bike is 3 times that, is 3 times X. Now, had we said this was X, then over here we'd have X divided by 3, and so just to avoid a fraction in my equation, I'm going to let X be the length of time that she ran. Now, here, eventually we want to, how far does she travel on her bike? We want to know this first. This is the number that eventually we're going towards. So as soon as we find the length of time that she runs, we'll plug that in, multiply it by 3 is the length of time that she bikes, times the 20, and it'll give us that distance. So we're not solving it directly. We're not, X is not our the variable that we want for our answer. So when we get done, when we have X equals, that's not going to be our final answer. That's just helping us to get to the final answer. So we've got 51 is equal to 60x plus 8x, or that x is 51 divided by 68. Right, so let's just leave it like that for a moment. We don't want round off error in our answer, so, and like we said, this time is in hours, so it's a fraction of an hour. It's less than an hour, and that's the time she spent running. Now, it wants how far did she travel on her bike. The distance that she went on her bike is the rate times time, a rate of 20 miles per hour on her bike, and she biked 3 times the length of time that she spent running. So this should give us an approximation for our final answer here. We've got 20 times 3 times 51 divided by 68. 45. That's nice. So 45 miles. That's how far she rode her bike. Now, out of curiosity, if we had the 8 times the 51 divided by 68. 6 miles is how far she ran, and the 45 plus 6 is 51, but that was the total distance that she ran and biked, her total distance. So yeah, it looks good. Alright. Yeah, okay, and that's the answer they have now. Alright, that I believe was the last one. So I hope this helped. Sorry I had to do it in 2 parts. I will talk to you later. Bye.